So our next speaker is Dr. Suman Paul from IISER Bhopal, and he will be speaking on strongly contracting geodesics in tree of spaces. Yeah, over to you, Suman.
Thank you, Shomoda, for inviting me to deliver this talk. Today, I will be talking about the strongly contracting geodesics in tree of spaces. So, in the first part, I will define what is a strongly contracting geodesic and what is a tree of spaces. And in the second half, I will describe our result in this direction.
Can you make it full screen?
Okay. Yeah. So let me start by defining the hyperbolic metric space. So a geodesic metric space X is called hyperbolic, delta hyperbolic, if there exists some delta greater than equals to 0, such that every geodesic triangle in X is delta slim. So what do I mean by delta slim triangle? So this is a definition of slim triangle. So a geodesic triangle is called delta slim if each of its sides is contained in the union of delta neighborhood of other two sides. So for example, take this triangle ABC. So we take delta neighborhood of AC and BC, then the third side will be contained in that. And this is true for all other sides also. And certainly this is not true in our usual Euclidean space. So in that sense, I mean, you cannot get a uniform delta so that all the triangles will be delta slim, right? Because triangles can get very fat. You can take big triangle and it will not, it will not be a delta slim. So examples. The first example is a tree. So this is the picture of a tree. So in tree, any triangle is zero slim. So what do we mean by that? So take 3 points A, B, C, and take the geodesic triangle. Okay. So the geodesic joining AC will be this line, right? And joining BC will be this line. And see that the geodesic joining AB is contained in the union, right? So this is in the union. So you don't have to take any positive delta. So at any tree is a zero hyperbolic. And the second example, it's the upper half plane, the Poincaré upper half plane with the Poincaré metric. Here, any triangle is delta slim, where delta equals to half log 3. Okay, and basically this definition of hyperbolic metric space come from the properties of H2. Okay, so H2 has this property. So we take this property and impose on in general metric space and call this a hyperbolic metric space. Okay. Now, now let me give some properties of geodesics in a hyperbolic metric space. So already we have seen it is the hyperbolic metric space is very different from what we know that Euclidean metric space. Okay, and so the geodesics in hyperbolic metric space will also be very different. So the first one, so this is the one properties of geodesics in hyperbolic metric space. So if you take two geodesics, which are 6 delta plus 1 distance away, then the projection of one geodesic to another geodesic has diameter 5 delta. Okay. So for example, if I take, so let me in the full screen and try to draw some picture. So if I take a tree, T, we know that it is a hyperbolic metric space. In fact, it is zero hyperbolic metric space. Now we take one geodesic, two geodesic, which is 6 delta plus 1 distance away. So here delta is 0, so 1 distance away. So take this geodesic and take this geodesic, say. So this is 2 distance away. Now, if I take the projection means nearest point projection. So the projection will be what? Projection will be, so let's say this is gamma 1 and gamma 2. So the projection of gamma 2 onto into gamma 1 is this point, right? So it has diameter 0. Okay. So this property is special about hyperbolic metric space. In fact, it is true also in H2 upper half. You take this geodesic and this geodesic. Okay, so we know the geodesics are vertical lines or the semicircle whose center is at x-axis. So then the projection will be always bounded. Yeah, this projection will be bounded. So this is a special property of geodesics in hyperbolic metric space. Equivalently, we can give this characterization of this property via this property. So via this, so any ball disjoint from a geodesic gamma has bounded projection into gamma. Okay, where the bound depends only on the delta. So what do I mean by that? So you take any ball which is disjoint from this straight line geodesic, and you take the nearest point projection. Okay, and then this set will be uniformly bounded for any ball which is disjoint from this gamma. Okay. Yeah. So now what we do, we impose this property of geodesic to a general metric space. Okay, and call those geodesic strongly contracting geodesics. Okay, so in a geodesic metric space, strongly contracting geodesics are generalization of geodesics in hyperbolic space. So the definition, so let sigma greater than 0, a geodesic gamma is said to be sigma strongly contracting if for any ball disjoint from gamma has bounded projection into gamma bounded by sigma. Same property. Okay. So we have already seen examples of strongly contracting geodesics, which are geodesics in hyperbolic metric space. But are there any, more examples? I mean, for example, if I take a non-hyperbolic metric space, can we find some strongly contracting geodesic there? So this is an example of non-hyperbolic metric space where there are strongly contracting geodesic. So let me first describe the space. So here we take one real line, okay, and at each integer per point we attach a flat Euclidean space R2, okay, at each integer point. So we get a space, geodesic metric space. And since there are flats, the Euclidean space are there, so it will not be a hyperbolic metric space, certainly. But see this red line, see this R. So this is a strongly contracting geodesic because if I take any ball disjoint from this red line, the projection is just a single point, right? So in that sense, it is zero contracting. So sigma is 0 here. Okay. And then can we get some non-example? Non-example in the sense that can we get a space where no geodesic is strongly contracted? Yes, we do have, and this is the standard Euclidean space where no geodesics is strongly contracted because of the obvious reason, right? Where you take two parallel lines which are far away, but the projection is not bounded, right? So yeah, so no geodesics strongly contracting. So now, what is the motivation behind giving such definitions? So the motivation comes from this fact that in a general metric space, we try to find some parts which look like hyperbolic metric space, and this is the starting point, right? So strongly geodesics for general metric space are hyperbolic part of those of that general metric space. In a hyperbolic metric space are important, and boundaries of hyperbolic metric consist. There is a motivation behind this.
Yeah, so there is some technical issue, I think, network issue. Let us wait for 1 or 2 minutes. He may rejoin.
Sorry about the glitch.
Yeah, you can share the screen again.
Right. Yeah. So where?
Yeah, maybe the last slide at the last part. Can you repeat again?
Right. Yeah. Right. So I was talking about the example and non-example.
Yeah.
And then motivation behind
Yeah.
the
motivation part was not very clear. Yeah.
Okay. So the first motivation comes from this fact that so the strongly contracting geodesics are hyperbolic part of a general metric space, so, where some properties of hyperbolic metric space are there. That is one motivation behind this, and other motivation is the boundaries of hyperbolic metric space are very important, and the boundaries consist of the geodesics of hyperbolic metric spaces. So similarly, we can define strongly contracting geodesic of a general metric space, taking the collection of strongly contracting geodesics on of that general metric space, right? So next, yeah. So this is the motivation behind this definition, and next we try to give the definition of this tree of spaces in pictures. So for that, we need to define what is a combination problem. Okay, so combination theorems are very important in geometric group theory, where we try to find new examples of these hyperbolic groups, relative hyperbolic groups, out of known examples. So basically, we start with a collection of groups, form a class, then we construct a new group combining the groups from this collection, and then next we ask whether the new group belongs to the same class. And here the class of groups are hyperbolic groups, relatively hyperbolic groups, and more generally conformally hyperbolic groups. And processes of combining the groups are graph of groups construction, or more generally complex of group construction. So in this kind of problem, what we do, so in geometric group theory, group are seen as a metric space. And what is the correct metric space for the group? That is the Cayley graph, right? So in dealing with this combination theorem, we consider a tree of spaces, which is nothing but the Cayley graph of the combining group. Okay, so and in general, we can give the definition of tree of space generally. So this is an example of tree of space. So what we do, we basically take a tree, any tree, and at each vertex, we add some spaces called vertex space. And at each edge, we add edge spaces. And then we glue along some embedding. Okay. So for example, so here the trees look like this. Like this, infinite. Okay. So now at each vertex of this, there is a flat. And the edge space here we take to be 1 point just. And then we glue via this edge. Okay. So these are the example of tree of spaces. Okay. So now there are some, then let me just give some combination theorem, which are important in our area, in this topic. So Kapovich in 2001 proved a combination theorem for asymmetrical graph of hyperbolic groups. I'm not going to the technical definitions. And Dahamani in 2003 generalized Kapovich's result for relatively hyperbolic groups. And in both this combination theorem, one part is common, that is the vertex groups are quasi-convex in the whole group. Okay, so quasi-convexity means, so it is convex, I mean close to convex. So means, so if you have a space X and some subspace, so Y will be called K quasi-convex. If we take any 2 points in Y and we join by some X geodesic, and then this geodesic lie in K neighborhood of Y. Okay, so basically generalization of convexity. So now in our context, the question will be, what conditions should we impose? So in this two combination theorem, so we take hyperbolic groups, or more generally, we can take hyperbolic spaces. Okay, and in Dahamani, they take relatively hyperbolic groups, and you can associate spaces to it also. Now, if I take general metric space, tree of spaces, then what about the vertex space? So what condition can be should we impose on tree of spaces so that the vertex space will be quasi-convex? certainly it cannot be done in generality. So we have done it for uh, strongly contacting geodesic. Okay, so we take a tree of spaces and we take a strongly contacting geodesic in a vertex space, which is we have already uh, told that this is the hyperbolic part of the metric space. So we consider this strongly contacting geodesic in vertex spaces, and we give some conditions so that this strongly contacting geodesic will be quasi-convex in the whole tree of spaces. So this is the theorem. It is joint work with my supervisor, Dr. Abhijit Pal. So the theorem is as follows. So basically, So this is a tree of spaces. This map X going to T. So X is a tree of spaces where all the A space are sigma contracting. You can say sigma strongly contracting and uniformly are separated. So basically we take these separate A spaces to be separated by some uniform bound R. Then we prove that this any strongly contacting geodesic in the vertex space will be quasi-convex. And one corollary of this theorem is that if we take P of uniformly hyperbolic metric space where vertex spaces are uniformly hyperbolic and H spaces are uniformly quasi-convex, then the vertex space will be quasi-convex in X. Okay, so this is outline of the proof. I will not, I will skip this. And another application we found, which is very interesting, that if I take, so X tilde to be the tree of delta hyperbolic metric space. Okay, so where all the vertex spaces are delta hyperbolic and H spaces are uniformly sigma contracting and are tilde separated, then the whole P of spaces will be hyperbolic. Okay, so this is kind of a combination theorem for combination theorem, right? Where we take so let me just draw. So we take some tree of spaces. Okay, so this kind of picture, so and this is going on, and where all these vertex space are delta hyperbolic, say, and these 8 spaces where there are gluing, those are uniformly sigma contracting. I'm not going into the technical details, and they are separated, uniformly separated. So that means this H space and this H space, the distance between them is R tilde. Okay, then we show that this whole thing, the whole space, okay, this is also a geodesic metric space, is hyperbolic, and which is very strange. I mean, so in Bezvina-Fehn combination theorem, the condition is very difficult to describe, Holloway flare condition. Maybe it is true in this case also. So that's why it is getting, it is giving you hyperbolic metric space. But there is a problem of this tree of spaces. We cannot use this result to prove something in group theory setting. Okay, because in group theory setting, in a combination theorem for groups, the T of spaces, in the T of spaces, the H space are one distance away always. Okay, so that's why we cannot use this in that setting. And we have used the Beigen characterization of hyperbolic spaces to prove this result. And the Beigen characterization basically says that so if you take any 2 points and you take a Beigen, so this is a hyperbolic metric space, then this Beigen is delta sleeve. Okay, and that is always true because the Beigen is regenerated triangle, but the converse is also true. Okay, so if all the Beigens are delta sleeve for some delta, then X will be hyperbolic. So is this characterization to prove this result? Okay, so yeah, so these are some references, and thank you.
Yeah, thank you, Shumon, for the nice talk. Any questions? So in the last result that you are having these R tildes, right? R tilde and like X tilde, T tilde. What are these? Can you just explain again?
Right. Yeah. So R tilde is a constant, depends on this delta and sigma.
Right.
Yeah. So delta is we choose first. Okay, delta and sigma we choose first. Then we get some R tilde, and this X tilde is the Q of space. So this whole space. So how do we define a Q of space? So this whole space is X tilde, and so why this is Q of space? There is a map from X tilde to some tree.
Right.
So T tilde is a tree. So the tree is like this, right? So for each of this space, we get one vertex, right, like this. And if there is a gluing, there is a edge like this. And this is going on.
So you're basically collapsing all these spaces to get the tree, right?
Right. And you can do the other way also. You can choose a tree, then you can define this tube space by associating vertex spaces and edge spaces and the gluing. Yeah.
And this R tilde separated means they're basically all these spaces are at least R tilde distance away from each other, or
No. So R tilde separated means this edge spaces in the vertex spaces, they are R distance away, R tilde distance away.
In the vertex space.
In the vertex. Yeah.
Yeah. Any more questions?
I have one.
Yeah, please go ahead.
So statement is that there exists R tilde. So I'm curious, is it computable in a sense that, you know, there's some sort of closed form formula, because very often especially in geometric group theory, whenever there's there exists the construction of that number relies on axiom of choice, which seems a bit cheating. So I'm just curious whether this is like
but the closed formula is there. I mean, not very difficult thing.
Okay, thank you.
You just defined contracting geodesic for ball outside the geodesic, right?
Ball
if you consider a ball outside your geodesic, then you can you take the projection that will have bounded diameter. Uniform bounded diameter.
Right.
So now if we can you consider instead of ball for all geodesic, who is let's say some distance apart from the given geodesic.
Right. That is the equivalent characterization, right? So I have told this. So this is one characterization. I'm not property of geodesic, and this property, this is again another property, but they are equivalent.
I mean, instead of considering ball, can you consider any quasi-convex subset?
Yeah.
Or
yeah. True.
Yeah.
So the delta will be bigger. Not delta, the sigma. Kind of.
Yeah.
Right.
Right. Okay. So if there are no more questions, let us thank the speaker again.